Hello, Baker fam. It's your science teacher, Miss Swenson. Sorry about the dog barking in the background. He's being in trouble. Anyways, I'm here to talk to you about this week's work and last week's work. I decided to combine them both into one video because why not? Anyways, so let's get right started. So this week is all about the other planets in our solar system, our whole solar system, and then also space exploration, what we can do to travel to other planets. So, here we go. So, there are 8 total planets in our solar system, right? There's a whole bunch of dwarf planets, and we have a ton of moons. So we have a lot, the sun has a lot of like natural satellites, but I want to focus mostly on the 8 planets because those are the ones that we can actually see when we look up into the sky at night, with the exception of, well, technically we can see Neptune. There's a trick to Neptune. All right, so let's talk the positioning of all of the planets. So here we go. We have all of the planets here, and the first planet closest to our sun is Mercury. Next is Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. So all of these planets orbit around the sun in a regular pattern, following a normal orbital pattern, which is what makes them a planet, right? They're large enough to have a strong gravitational pull, maybe to have their own moons, and they're following a normal pattern, which is why a lot of the dwarf planets get booted out, because they don't have regular orbital patterns. So, there are 2 belts. I'm going to go back here. We have the asteroid belt, and that is between Mars and Jupiter. And we have the Kuiper belt, which is at the end of our solar system as we know it. The first planet in our solar system is Mercury. Mercury is the closest planet to our sun at 0.4 astronomical units, right? So that's what the AU is. AU is 150 million kilometers from the sun, or that's the unit of measurement. That's what I said about like an astronomical unit being massive. So from the sun to the earth is 150 kilometers, and we call that an astronomical unit. It's just easier to say astronomical unit than it is to say 100,345,620,052, right? It's just way easier to say an astronomical unit than it is. And it's a lot like scientific notation when you're in math, where you're trying to take these huge numbers and then put them down into a easily definable, easily put on paper number. So, Mercury, even though it is the closest planet to the sun, it is not the hottest planet. That goes to Venus. Sometimes, because Venus is on the other side of the planet, right? And we got the sun, we got the earth, and it's traveling around. Sometimes when the one planet is on the other side of the earth, and all I have is nail polish right now. Sometime when the other planet is on the other side of the earth, these 2 planets become close to each other. Right? Closer to each other. And you're like, wait, Miss Swenson, why is Mars not closest? Well, same reason. Sometimes, depending on what's going on in its orbit around the sun, sometimes Mercury is our closest planet. So, a Mercury year is only 88 days long. That means it only takes 88 days for Mercury to travel entirely around the sun. It only takes 88 days. And I'm pretty sure it has a very small rotation, so it takes about that long to travel around. It's a lot like the moon as far as rotation, day rotation. It is the smallest and densest planet. It is a lot like Earth as far as density goes. The next planet is Venus. Venus is the second planet from our sun. It is 0.7 astronomical units away. The hottest planet in our solar system by far. It's super hot, right? 900 degrees Fahrenheit. That's toasty. I was complaining about the weather in one of my other videos. Nah, nothing compares to this. For the longest time, people thought Venus was going to be our next planet to travel to because it had an atmosphere that was similar to Earth's, and it had a size that was similar to Earth's as far as we can see from telescopes. When we actually were able to analyze the particles on Venus, and how we do that is we can shoot beams of light, and through refraction we can actually see the particles, what color the particles are. And so we shoot it there, it bounces back to us. We can actually see what the atmosphere is made out of, or the surface materials, and well, not good. The clouds are made of sulfuric acid. Yeah, the stuff you put down drains to clear out the hair in them, and it is unless you have a septic tank, don't put sulfuric acid down there. I don't think sulfuric acid is good for normal sewers, but I know they use it to clean drains sometimes. They use it to etch metal and glass. Anyways, so the clouds are made of sulfuric acid, and it is 900 degrees Fahrenheit. That is not livable for us. I was like, the fact that it has free water molecules, and it's got an atmosphere, and it's got a similar size, which means it's got a similar gravity, we just can't live on it. It's not possible unless we find some way to counteract the temperature, which it's really hot, and we have ways to do that, but how do we get our machines and devices and so much materials there and protected is a really good question. So a Venus year is 225 days, but a Venus day is 243 Earth days, which is in part kind of plays why it's so toasty, because as you know, as the Earth is spinning, right, some of it's spinning, the parts that aren't lit by the sun are actually the heat is being released from it. So imagine one side of the planet literally being toasted all year long, and then some. So it takes a long time for Venus to turn, but relatively shorter year than us. The Earth is the next planet, the third planet from the sun. I'm not going to go into this because we've already been spending a lot of time on the Earth and what the Earth's about. The fourth planet from our sun is Mars. Mars is 1.5 astronomical units away. It is red. The redness is because of the iron oxide on the surface. If you've ever seen a car and a car driving, or rusty boat, right, rusty metal boat, or any kind of like rusty nail, that is the iron oxide on the surface of the nail, which causes it to have that red tinge to it, and that's the reason why Mars is red. Mars is about half the size of the Earth, which, if you know anything about mass, which you should, the more massive something is, the more gravity it has. And in the same turn, the less massive it is, the less gravity it has. This will cause it to be less gravity than Earth. So we will feel a little lighter. Anyways, Mars has a year of 669 days, and Mars Day is pretty close to an Earth Day, right? It takes 24.6 hours to turn all the way around. As it's traveling, it's 669 days around, almost 2 years, a little less than 2 years, but all the way around. Mars is very cold compared to Earth, right? So on one side we got Venus, who's very toasty, and the other side we have Mars, which is very cold, but not so cold that we cannot approach it, right? So it's only in the negative 60 degrees Fahrenheit area-ish, right? So that's really cold. That's below freezing, but it's not. Our body heat and the things that we have the ability to travel there and keep us warm and at a level temperature, realistically. It's a lot easier to heat things than it is to cool things, if you know anything about air conditioning in your house, right? You feel a lot better during the wintertime bundled up than you do in the summertime when you can't get enough clothing off. Our next planet is Jupiter, right? So remember, in between Mars and Jupiter, there's that asteroid belt, and there's about 4 dwarf planets in there, but I'm not going to go into dwarf planets. Just know that they're there, and if you're interested, go look for them. Jupiter is about 4.9 astronomical units. It is the largest planet in our solar system, and it only takes about 10 hours to rotate, which is really, really, really fast if it's the largest planet in our solar system. And this kind of aids to the creation of the mini storms on the surface, right? When you have something spinning that fast and you have a bunch of gas on the outside of it, you're gonna get some competing convection currents, and it's going to create storms on the surface. One of its major storms right here, right? We have the red eye there, the big giant storm on Jupiter that actually we can see about every 10 hours, right? Jupiter's year is 12 Earth years. That means it takes 12 years for Jupiter to travel around the sun. Jupiter has little to no seasons. And what do we know causes seasons? So what causes a season? So what does that mean about Jupiter? Next up, Saturn. Saturn is the 6th planet from our sun. It's 10.9 astronomical units away from the sun. It's known for its visible rings, right? So everybody knows Saturn. When we go to draw planets, when we're young, when we go to draw a planet, we don't, unless we're drawing Earth on purpose, we usually draw Saturn. We draw the circle and the rings around it. Saturn is known for its visible rings. A Saturn year is about 29.5 Earth years, and a day is 10.6 hours long, slightly longer than Jupiter, just a tad. So it's still moving really fast. Another cool thing to note about Saturn is if you notice it's kind of smushed, right? So it's got a really strong gravitational pull in this ring here, and it actually is a little lopsided because of that, right? So not that you ever have tried this, but if you take like a hard-boiled egg and you spin it, it'll actually squish and flatten, right? It'll become more round and it will become flatter because the energy will be expelled, right? So that force will just push everything to the side. And so Saturn here, because it has so much mass on this ring here, it actually spins really fast and squishes it down. Saturn has seasons very similar to Earth's. They've got storms and weathered patterns that are very similar to Earth. So, again, what does it mean when a planet has seasons or doesn't have seasons, right? Refer back to our lesson in, the YouTube video. I'll link it down below. So you can determine what causes a season on a planet. of the cool things about planets is that they all run on the same rules, right? It's this system of movement around the sun, right? All of these other scientific phenomena and reasonings are playing a part in why the planets are doing what they're doing. So we can actually pinpoint why something happens. It's really cool when you think about it. Uranus is the next planet, 7th planet from the sun. It is 19.2 astronomical units. One thing it's not known for, but is known for, it's actually got invisible rings. We can actually see that Saturn has these rings around it. It's just not as defined, or Uranus. Uranus's rings are not as defined as Saturn's rings. But it's got this beautiful blue color. Look at that. It looks like I literally took one of those 3D print things and plopped it on there. Pretty blue color. You can actually see a little bit if the video is good enough definition. You can actually see like little storms in there, right? You can actually see the streaking of different materials. Uranus's year is 84.02 Earth years, right? 84 years. Literally, astronomers have been staring at this thing for thousands of years. And they discovered it takes 84 Earth years. That means an astronomer probably lived, grew up, looking at this one planet, up in the sky, right? Seeing Uranus up there for his entire life. Just slowly moving, right? But the good thing is not everything's run on the same system, right? So that's how we can kind of tell where we are in the universe, right? Because this thing is moving slower. Well, not slower, but it's taking longer for it to move than the other planets in our solar system, which shows us that we are moving in a similar pattern. So it's kind of cool to think about how long it takes one of these things to travel around the sun. A Uranus day is about 17 hours, so little slower, so you're not going to see as strong as storms. And then Uranus has only been visited by one Earthen spacecraft, which is the Voyager 2. That we know of, right? Who knows about I shouldn't say terrestrial. I mean, it could be. They could have come from Mercury. In case you didn't know, terrestrial planets are the first 4 planets in our solar system, right? So that's Mercury, Venus, Earth, and Mars are considered terrestrial planets. A lot of the reason for that being is because they are solid. They are made of rock-type materials, and those rock-type materials are they are solid in hotter temperatures. For instance, like this is not melted at the temperature that we are right now. There's a lot of things around me, like for instance, the sound that you're hearing right now or the light that you're seeing is going through gas, right? And gas is a gas at a temperature that the Earth is, right? So at like, what is it right now? 70 degrees outside right now. 70 degrees is how 70 degrees is the temperature at which the air around us is gas. And plastic, which is made of similar things, right? Everything's made of atoms and matter, are solids. So terrestrial planets are defined by the fact that they can be solid closer to the sun. Solid, and as you know, closer to the sun doesn't necessarily mean temperature is hotter, because Mercury's not the hottest planet, right? By that idea, Mercury would be the hottest planet. But a little further away, right? So in a higher temperature, these things can be solid. So like iron, right? Think of how hot iron has to get in order to be melted. Or like stone, right? I do pottery. Maybe I'll make a video of it, but I do pottery, and it literally, I have to cook it at 2,000 degrees temperature for it to harden, right? To become a solid. And if you're thinking, what? So you actually melt it down a little, and then it becomes a solid after that. But it doesn't lose its form, which says it doesn't become entirely liquid. Just the particles in it become liquid. I'm getting on a rant. Welcome to Miss Swinson's science class. If you were in class, this is exactly what would happen. Anyways, back on topic. This is not correct. This is supposed to be Neptune. Ooh, let's fix that. Yes, Neptune. Okay. Yay! Back to Neptune. Anyways, so, Neptune is the 8th planet from our sun. It is 30 astronomical units away. A lot of time. Right? There's a long time. Probably would take... you know, 5 hours or something for light to travel to Neptune. That's a long time when you're thinking it only takes 8 minutes to travel to Earth. Anyways, it was invisible to us until 1846, and not actually invisible. It was often mistaken for Uranus. So what would happen was Uranus was traveling around, and since this is a pretty blue planet too, not that you can really see the difference in color unless you have a microscope, but up until 1846, it was traveling around, and you got to think, it takes a long time, right? It takes someone's entire lifetime to watch this thing. So all the documentation is saying that Uranus is moving in a particular pattern, right? So they can see it, they notice it, they're looking at it, and it's moving in a particular pattern. They notice that this planet, which they thought was Uranus, is not following a normal orbital pattern. It's not the same distance away. It's not the same orbit. It's wonky, right? And so it wasn't until 1846 that they're like, uh-oh, we've actually been looking at another planet. So they named this one Neptune. Neptune is the 8th planet from our sun. I would find it really hard to believe that we find another planet after this one, but maybe there is another planet after the Kuiper Belt. Possibly. Who knows? Maybe one day you guys will grow up. When you guys grow up, you guys will create the next space satellite that will show us the next planet, because that would be really cool. Or maybe you'll show us that we all are in a gigantic orb with holes poked in it. And we're someone's ant farm. Anyways, so Neptune's year is 164.8 Earth years. Think about that. In order for someone to track Neptune, it would have to go through generations of people. Think like 12 years old, you can probably start investigating this stuff. And then you'd have to start training your apprentice to do the same thing when they become of age to do that. I mean, you could technically do it younger age. 7 years old, I assume, could be looking up at the sky and documenting properly the information that you see. But 164 Earth years takes to travel all the way around the sun. That means someone had to watch this planet for 200 years to know that it does the same thing. That it follows the same pattern. You can average it, you can assume, right? You can hypothesize based on speed, trajectory, all this other fun stuff. But that's a long time to wait to test your hypothesis. And that's science sometimes. Its day is 16 hours long, and it's also this beautiful blue color. Look at how pretty this planet is looking at this. Oh, man. Beautiful. All right. So, space is massive, right? So we just went over the 8 planets in our solar system. It's a gigantic, massive, huge thing, right? We measure it in astronomical units, right? 150 million kilometers to the sun is considered an astronomical unit. That's how we measure things in our solar system, right? We can also measure things in light years. That's how long it takes light to travel a year. Think about it. Our sun's light takes like 5 hours to travel to like Neptune. 5 hours. A light year is how long it takes a light to travel a year. Yikes. That's a long... I can't believe that number is even like used. This idea is like beyond me. Anyways, so our moon is 365, you can round it up to 366 kilometers away to 406 kilometers, right? Because it's not perfect. Orbits aren't perfectly round. They're affected by gravitational pull, the sun, the earth. So there's so many things that have to do with how close our nearest satellite is, and that is the moon. It took Apollo 11 almost 9 hours to get to the moon after using the Atlas V rocket. Right? This Atlas V rocket accelerates at about 16.26 kilometers per second. Kilometers per second. That's a lot. That's a whole lot. Fastest man on Earth only ran 307.58 kilometers per hour, right? That's Bolt. And the fastest jet plane is 3,529.6 kilometers per hour. And if you were to relate that to how fast this rocket was going, I cannot believe those astronauts survived that. Like, I could just imagine how many G's were pulling your face back. Anyways, 0.9 kilometers per second. Right? 16th of the amount of speed that the rocket was accelerating these astronauts to the moon. The fastest plane we've ever created only does a 16th. Okay? Not rocket science. Or is it? Right? Apollo 11. I wanted to show you guys some pictures of the Apollo 11 mission. It's such a huge part of our history. I'm not going to get super into it because that's not the focus of the lesson. But so here's the Atlas V rocket right here, right? And you can actually see the second rocket blasting off from the first rocket, which we'll talk about rockets in a sec. And this is the mission that put the first men on the moon, right? There were 3 men. We've got Buzz Aldrin. What's his first name? Edwin Aldrin, which is Buzz Aldrin. We've got Michael Collins. We've got Neil Armstrong. And if you guys didn't know, he's the first man on the moon, right? They went there. They were so impactful. They took back a whole bunch of samples. Look at these spacesuits. They had to basically be in these spacesuits all day long. I'm sure when they took this picture, they were like, yeah! And then when they got back to take another picture, they're like, get me out of this thing, right? So they're entirely encapsulated in these suits. They've got a breathing apparatus. They've got temperature control gauges. They've got places to go to the bathroom, all up in this spacesuit here. So this is the Eagle right here. This is the thing that actually touched down onto the moon. A lot of it is still there. So when you go see things at the museum, they're usually replicas because we were very wasteful and there's not much we could have done that wasn't wasteful. We weren't aware of how wasteful we are to the environment back then. We're a lot more aware now. And so a lot of this stuff is left there. Only the top part actually removed itself and they traveled back with it. And this whole thing is crazy technical. But they brought back a ton of samples. We have a ton of rocks from the moon. We have a ton of samples and firsthand experiences, what it was like. There's a lot of cool things. If you ever want to be entertained and you're interested in moon space travel, look up what could have gone wrong on the Apollo 11, because the amount of luck that these guys had, right? The amount of stuff that broke, the amount of warnings that flashed, all of these things, like, these guys are cool. I would love to be an astronaut. That would be amazing. All right, so let's talk about rockets. Yes. So a big part of space travel is how to get the astronauts into space, right? Because if everybody could fly, we would have done it already, right? So a lot of it's technology, and hopefully when you guys grow up, one of you becomes a rocket scientist, and then you guys can be like, Miss Swenson, that dream that you wanted to go see a rocket is like, I'm bringing you there. And I'll be like, yes, let me smell the rocket fuel. Anyways, don't sniff rocket fuel. Don't do it. Anyways, so right here we've got the Atlas V. That's the rocket, and the top part of the rockets up until recent times, because obviously this one, the shuttle, is on the outside. The top part of the rocket is the only rocket part that the people are in. The rest of this here, the rest of all of this is just booster fuel to get it out of the atmosphere. To get this stuff away from the gravity of the Earth and put it into the space. Put it in orbit, right? So your first section right here, probably the most expendable section. It's just like a giant tank of gas. And the way they funnel it is, if you notice, all of these have like a little tiny, I don't know what you call it, flange there. And it's made so the gas is actually pushed out. So as it ignites, it actually pushes it out with a ton of force, right? You can cut things with water by putting water through a funnel small enough to create like a laser type beam. So you can cut things with water, and they do it quite often. And so we've got the first stage here, and this first stage is basically all fuel, right? It's got a little parachute in it. So when it falls out of the atmosphere, it doesn't hurt anybody. So it's got this fuel here, the fuel shooting out. When it gets done, when it gets to the second stage, this part here actually blasts off of this original part. So we've got the boost from this one, then we've got the boost from this one here, which should get it past the, we've got atmosphere here, stratosphere, and if you remember, the layers of the atmosphere are the layers of our Earth's atmosphere from the beginning of your 8th grade year. But this boosts it off, right? Pushes off of this one. This one deploys a parachute, falls down to the ground. This one also does the same thing, right? Gas shoots out here, propellant shoots out here, and then parachute falls down. And then this one here is the last one. This one shoots the rocket into where it's gonna go, right? So it's almost out of the atmosphere, correct angle, shoot it forward. And because in space there is no resistance, right? So in 7th grade we talked a lot about force and motion and how like the resistance of air causes you not to travel through it, right? We can't fly because, or we can't fly fast because there's a resistance, right? It'll create heat and blow stuff up. But so it'll shoot it out, and in space, because there is no atmosphere, there is nothing in there, you will just glide to where you're supposed to go. Which is why it is so important for you to know the trajectory of your rocket ship before you fly off, because it's a little harder in space to control where you're going. And I seriously can't believe how much technological advancement happened in such a short amount of time. But we got people up there now. And this is how they flew up there. That last one there. And they've got the SpaceX. That is your tidbit of information that has to go with your last 2 weeks of assignments. So last week I asked you on the one-pager to create a poster or a picture or color the picture on the back of some of the properties and attributes of each planet and how far they were, maybe how big they were, what they look like. And so I asked you to make a poster last week of that. This week, I'm asking you to do, you are going to use the silhouette on the backside or draw your own. You are going to create a spacesuit in which people are going to be able to live out in space or travel to a different planet. And you're going to take some of the problems that we have and we know of that have to do with space travel, right? Maybe you are going to create a spacesuit that protects, it's like armor, right? So you can do a spacesuit that protects against the rocks and debris, because if you don't know, other planets, especially ones without a really strong atmosphere, don't have ways of smoothing the rocks out. So if you look at a lot of the rocks on Earth, they're nice and smooth. The rocks on other planets are actually really gritty and they aren't smoothed out, right? So they're really jaggedy. So maybe you're going to create a spacesuit to save that. Oxygen, water, how are people going to live on another planet, right? So what's your spacesuit going to include that solves for those things? What about temperature? What about movement, right? What's the point in having a spacesuit? What's the point of even going in space if you just have to sit there like this? Like that kid on A Christmas Story. All right, that's all I have for you today. You guys have fun creating your spacesuits and your solar system posters. Post them on Teams, email me, call me and let me know what's going on. Show me your learning. Thank you. Have a good day.